Hello viewers, welcome to the Reactive Intermediate course. Uh, in this lecture we will discuss about Aryne or Benzyne. This is the introduction of Aryne or Benzyne. Aryne or Benzyne are derived from aromatic ring by removing any two substituents. So this is also called, by removing these two substituents, this is also called dihydro product of Arynes. They have characteristic triple bond in their structure, so that is why we call it Aryne or Benzyne. So it ends with this suffix yne in aromatic ring. So this is the brief history. This Aryne or Benzyne first postulated in 1870 to explain biphenyl formation. Then Wittek proposed the mechanism to prepare benzyne in 1940. Then the classical labeling experiment by Robert in 1953, Dizelder trapping by Wittek in 1955 to prove that benzyne really exists, and then finally its general formula of benzyne is C6H4 with, you can see, one triple bond in its structure. So this is Aryne or Benzyne. If Aryne having hetero atom or atoms in their ring, they are called heteroaryne. For example, this is the simplest benzyne. For example, this is a structure is similar to pyridine with one triple bond here. So at 2 and 3 position, this is called 2,3 pyridine. So 2,3 pyridine is an example of heteroaryne. This is a similar structure with pyridine, but they have this triple bond here at 3 and 4 position. So this is called 3,4 pyridine. This is 2,3 thiophene. This is structure is similar to indole. So this is called indoline, and this is a naphthalene type structure, but with here at 1,2 position, it's here triple bond here is called 1,2 naphthalene. So benzyne are very reactive, and they are studied through special techniques like matrix isolation techniques, laser flash photolysis, and some specialized mass spectrometric techniques like ion cyclotron resonance MS. So this is the structure of the benzyne. Benzyne, here you can see in the benzyne one triple bond. Here you can see in each one electron in this orbital, then through the parallel overlap its triple bond here exists. So normal bond angle in the alkynes is 180 degree. So in case of the benzyne, this angle is 120 degree. So you can see this in the alkynes normal angle is 180, and in the case of the benzyne the angle is 120 degree. So these benzynes are highly strained. So here these are the resonance form of the benzyne. This benzyne can be shown in dipolar form. Here these dipoles are formed on this benzene ring. So this is the structure of the benzyne. In normal alkynes, this bond angle is 180 degree. So this alkynes are normally linear molecules, and they have the bond angle of 180 degree. So in the case of the benzyne, here you can see this is one electron if comes in each of this orbital. This is sp2 hybridized orbital. So through this parallel overlap, here we can form a triple bond here. So in the case of the benzyne, the bond angle is 120 degree. So you can see from this as this alkynes are linear, so you can see this 120, this benzyne is highly strained molecule. So these are the resonance form of the benzyne. Here you can see the dipolar structure of the benzyne. We can show here the dipoles, negative and positive. We can also show the benzyne in the form of this triple bond. Here this is a chemolene type structure, and we can show the benzyne as a biradical, orthobiradical here, and even the experimental evidence also show that the benzyne can exist in metabiradical as well as in parabiradical. So these are the resonance form, you can say resonance form, canonical forms, or hybrid structures. So real structure of the benzyne is average of all these structure. So this is these are the experimental evidence that this benzyne intermediate really exists. So in this here, this is 1-chlorobenzene. Its position 1 is labeled with C14, and it is treated with strong base potassium amide in liquid ammonia. So this NH2 attacks on and takes this proton. So it generates here carbanion. It's later on this carbanion, this charge comes here, and then this chlorine is chloride is removed to make this orthobenzene intermediate. So now this orthobenzene intermediate, this nucleophile ammonia can attack here or on that carbon which is labeled with the C14. You can see here this carbon which is labeled with C14, it is called ipsocarbon. So if this ammonia can attack on here ipsocarbon or on this adjacent carbon which is sine substitution. So we can get two types of the aniline, one with the ipso substitution and other with the sine substitution. They are formed in almost 1-to-1 ratio. Ipso substitution substituted aniline is 47% in yield, whereas the sine substituted product is 53% yield. So these are formed. This shows that a symmetrical intermediate like orthobenzene is formed, which is from where we can justify that these two products are formed in 1-to-1 ratio. This is nucleophilic substitution aromatic. Previously it was believed that this NH2 can directly attack here and we get this aniline in 100% yield, but this is not the case. We get these two products in almost 1-to-1% yield, which shows that the asymmetrical intermediate like orthobenzene is involved. So this is the experimental evidence which shows that orthobenzene really exists. So ipso and sine substitution through orthobenzene intermediate, we can justify this mixture of two types of the substituted anilines. So Aryne or benzyne can be synthesized by using halogenated arylated compounds. Here in this case we use here strong base like lithium diisopropyl amide or LDA. This take is used to take this proton, and then this bromide is eliminated to form this 1,2-naphthalene benzyne intermediate. So this after taking this proton, lithium diisopropyl amide eliminated as after taking this as lithium diisopropyl amine. So this is another halogenated aromatic compound. Here magnesium turning is used in the presence of tetrahydrofuran at low temperature. We make the Grignard reagent here, and then this Grignard is eliminated to form this benzyne intermediate at low temperature. So these are the two examples of dihalogenated aromatic compounds. Here this 1,2-dichlorobenzene, when reacted with this magnesium turning, it will almost same type of reaction. It forms the benzyne intermediate with the elimination of magnesium dichloride. This is diiodobenzene, 1,2-diiodobenzene. It is heated to form this benzyne intermediate. So this is an example when two possible Arynes intermediate formed from single precursor. Then that Aryne will be formed which has stable carbanion. So for example, this is a 3-methoxy-1-bromobenzene. When it is treated with strong base like sodiamide, then this sodiamide can take the proton from this or from this. So it generates two types of anions. If it can generate anion here, This anion is ortho to this methoxy. This methoxy is electron withdrawing group. So this anion is more stable due to negative inductive effect of, or electron withdrawing inductive effect of methoxy group as compared to this anion. So this carbon ion is more stable, so that we can have then this Aryne intermediate. So this is another example. In this case, this is here this instead of methoxy is methyl group. So methyl is electron donating group. So this anion is more stable because this is formed away from this methyl group. So this anion is more stable. So we generate this type of Aryne intermediate after when this charge comes here, this bromide leaves. So when there are two possibilities for the formation of Arynes, then from single precursor, then that Aryne will form preferentially or predominantly which has stable carbon ion. So the benzyne intermediate can also be generated from direct lithiation. So here this example, you can see here fluorobenzene, when it is treated with phenyl lithium. Phenyl lithium is a strong organic base. So this phenyl lithium, this phenyl takes this proton and make here lithiation. Let's do the direct lithiation here. So after that, elimination of lithium fluoride is eliminated and generate this benzyne intermediate. This is another example where this lithium mercury amalgam is used, and this again direct lithiation at this bromine position, and then this lithium fluoride is eliminated to generate benzyne intermediate. So this is the direct lithiation of halogenated aromatic compounds. So this is another method in which 2-trimethylsilyl triplet is used in the presence of cesium fluoride. So this method, here this trimethylsilyl, this fluoride ion attacks on this trimethylsilyl, and then this 2 electron shifted here, and then this trifluoromethyl sulfonyl is eliminated to generate this orthobenzyne intermediate, and this one cesium triplet and trimethylsilyl fluoride. So this is another way. This is again same cesium fluoride. It's same, it attacks on this trimethylsilyl, this 2 electrons shifted here, and then this trifluoromethyl sulfonyl is eliminated to generate this 1,2 naphthalene. So this Aryne is generated. So this is another method. We can generate benzyne intermediate through anthranilic acid. This anthranilic acid is 2-monophenyl benzoic acid. When treated with sodium nitrite in the presence of hydrochloric acid, is formed this nitrous acid. This nitrous acid, if you see, this is sodium nitrate structure. When it takes the proton, it forms the nitrous acid. Then this nitrous acid again takes a proton and then this water molecule is eliminated to generate this nitrosonium ion. This nitrosonium ion reacts with this amino moiety of anthranilic acid to form this diazonium salt. So this diazonium salt in the presence of a base and heat, it's decarboxylate here, and this will generate this sodium salt of carboxylic acid is decarboxylated, carbon dioxide is removed, and these 2 electrons shifted here to make this benzyne intermediate, and this nitrogen is eliminated as a gas. So this is the one method through which the benzyne can be generated starting from anthranilic acid. So another way to generate the benzyne intermediate is through Diels-Alder reaction. In this case, this is the 4+2 cycloaddition reaction. Here we use the 1,3-diene and alkyne. This is reaction between 1,3-diene and alkyne to form the benzyne intermediate through Diels-Eld reaction. So the benzyne or Aryne can be generated by using 1-amino-benzotriazole. 1-amino-benzotriazole when treated with lead acetate, it's give this type of intermediate, and then this elimination of the nitrogen gas to generate this benzyne intermediate. So it's also thermal decomposition of benzothiazole 1,1-dioxide results in formation of benzyne intermediate, and nitrogen gas and sulfur dioxide gas is eliminated. So this is another method to generate the orthobenzyne intermediate. So the benzyne intermediate can be generated from hypervalent iodine compounds. So this is phenyl iodinium carboxylate. This is commercially available. When it is heated or refluxed in the presence of diethylbenzene, decarboxylation occur here and it generates the benzyne, and this iodobenzene is eliminated along with carbon dioxide. So this is another hypervalent iodine compound. This is called phenyl 2-trimethylsilyl phenyl iodonium trifluoromethyl sulfonate. So this when treated with tetrabutyl ammonium fluoride, so this fluoride ion attacks on this trimethylsilyl moiety, and then this charge shift over here, these two electron, and then this carbon hydrogen bond breaks, and then this trifluoromethyl sulfonate is eliminated along with iodobenzene, and trimethylsilyl fluoride ion is eliminated, and it also generated the benzyne intermediate. So this is another method to generate benzyne intermediate. This is through photolytic generation of benzyne intermediate at low temperature. So this compound, this is a dione. This compound under photolysis gives this cyclopropanone type intermediate with the elimination of carbon monoxide. Then this intermediates again photolytically decomposed to form the benzyne intermediate with the elimination of carbon monoxide again. So this is another compound. This is a benzodioxane 1,4-dione. When it is decomposed in the presence of light, it gives this lactone intermediate, and this carbon dioxide is eliminated. This is carbon dioxide is eliminated, and this gives this lactone type intermediate, which again decomposed in the presence of light to form this benzyne intermediate, and carbon dioxide is eliminated. So this is another compound. This is 3-diazobenzofuran 2-one. This is decomposed in the presence of light to form this benzyne intermediate. Carbon dioxide is eliminated along with this simplest carbene is eliminated, and nitrogen gas is eliminated. So this is another compound. This is phthalic anhydride. Phthalic anhydride is decomposed in the presence of light to form this benzyne intermediate, and carbon dioxide and carbon monoxides are eliminated. So students, this is the summary of the generation of benzyne intermediate. So first method which we discussed is the generation of benzyne intermediate from halogenated aromatic compounds. So in the presence of strong base like sodamide, n-butyl lithium, lithium diisopropylamide used as base to generate the benzyne. This is the second method in which dihalogenated aromatic compounds has been used to make the Grignard reagent, and then this Grignard reagent elimination occur to generate the benzyne intermediate. So this is a direct lithiation method in which we use direct lithiation of this halogenated aromatic compound. Then this trifluorosulfonyl or triplet is removed to generate the benzyne intermediate. So another method which we discussed is hypervalent iodine compounds. Hypervalent iodine compounds, when we use butyl ammonium, tetrabutyl ammonium fluoride ion, then this 1,2 disubstitution on this aromatic compound, fluoride ion remove this to generate the benzyme. So this is another method in which trimethylsilyl and triplet is a good leaving group, and this fluoride ion is used to generate the benzyne intermediate. So these are the other two methods in which 1-amino benzotriazole is decomposed to generate the benzyne. This is another one method. So this method in which anthracyclic acid is used undergo the reflux or heat to generate this benzyne intermediate with the loss of carbon dioxide and nitrogen gas. So this is a summary of the different method which we studied for the generation of benzyne intermediate.